So now, I think they're just getting set up here, but I'd like to introduce John Su and Nate Koenig. They're speaking about Gazebo in general, and I know there's been a lot of interest in that as well recently, and it's good to have some of the original and continuing developers available to discuss it. All right, thanks.
So I'll get started while John's setting up. So I'm Nate Koenig, and I've been working closely with John for the past 2.5 years now, working on developing and maintaining Gazebo. So we're going to indulge you with lots of good Gazebo stuff. We're going to basically talk about overview of Gazebo, exactly what it is, why you should use it, which is a very important feature, and then I will delve into some more of the details about the architecture of Gazebo, creating your own world, your own environments to do interesting things with robots. John will come over and take charge of developing robot models itself, and we'll go into how you can write client code to interface with Gazebo and do fun and interesting things. So Gazebo started about 10 years ago down at USC. It was originally developed as a tool to accurately simulate, or as accurately as we could, simulate outdoor environments for projects that we had going at the time. So also during this time, Player was the one big game in town, so we obviously built interfaces for Player. Since then, we have grown to incorporate both ROS and also support your own custom code that doesn't need to exist in ROS or in Player. So over the years, people have done very interesting things with Gazebo, from developing models of eggs so that you don't destroy your fancy new PR2 by squishing eggs. And so they developed a nice model of eggs that would break if you applied too much pressure, and developed controllers for a gripper. One of the first projects to use Gazebo developed learning gates for hexapod robots. And they used this to both visualize the results and evaluate how well they performed. So complex indoor environments can be set up, such as indoor factory settings, where they use this environment to test controllers for mobile robots and industrial arms and grippers. You can also use multiple robots, such as soccer, or do coverage analysis by dispersing robots in indoor spaces. And finally, you can, of course, use the PR2 to do complex motion planning and mobile manipulation. So I'm going to go into a little bit more of how Gazebo is set up and how it runs. So historically, Gazebo was a monolithic system. It was basically wrapping a physics engine with some visualization code and interfaces to give you a convenient access to generating sensor data, having actuators do interesting things in the environment. Over the years, it got more and more complex, and this spurred us to do a massive rewrite, which is now Gazebo 1.0. So we've separated out the server and the client, trying to take advantage of better threading models, better support for multi-process execution. So the server, you can think of this as just running a physics engine and data generation. And the client can be anything from the GUI that we ship with Gazebo to your own client code. And there's multiple ways that you can talk to Gazebo. One of them is via socket communication, and another way is through plugins. And we'll go into those in a little bit more detail later on. We've simplified this plugin interface. So before, it was this complex set of controllers that you'd have to define in a very rigid architecture. Now you have a very open plugin API, which lets you control any aspect of Gazebo, from forces applied to bodies to gravity and various world properties. And finally, we rewrote the description format for Gazebo so it more closely matches URDF, with a few extra features for things like defining your scene and your lighting models and things like that. So there's 4 basic components to Gazebo, as you could probably guess from what I've been saying. There's a physics engine, and historically we've been using ODE because that was the physics engine around at the time. So we still support ODE, and we're about 80% into getting Bulletin, which will be nice to have a comparison between these two engines. For rendering, we've always used OpenGL. We've moved on to Ogre, which has a lot of nice features, lets us integrate some new fancy game-based technology into Gazebo itself. In terms of interfaces, I've mentioned we have plugins and inter-process communication, which uses Google Protobuf and Boost ASIO to do socket-based communication. And finally, a set of user interfaces, the primary of which is Qt, but we also have this ability to support your own custom GUIs within Gazebo that act as overlay in OpenGL through the CE GUI library. So what this looks like in a running system is after a little bit of initialization, Gazebo essentially just runs through a loop of updating physics, generating sensor data, and then communicating with some external client and sending data back and forth. And on the client side, the client is extremely lightweight and simple, just getting user input through some GUI and visualizing data from the system. So you can replace this client with anything you want. It doesn't have to be our GUI. You can create your own thing, whatever it is, and talk to the running server through topics. So I'm going to go into developing model environments for your robots, and this is fairly important because you want your environment to ideally match what your robot is going to operate in so you can get good data out and test your algorithms properly. So your environments can range from very simple to very complex. So if you're interested in focusing on a very specific aspect of an algorithm, you can create a very simple environment with a ground plane and a few boxes and just quickly iterate over a particular feature that you're concerned about. If you're interested in outdoor environments, aerial robots, legged robots, that type of thing, you can create terrains and simulate outdoor environments realistically. And finally, you can create indoor environments. In this case, we just extruded the map, the blueprint of Willow Garage, and we use this fairly regularly to do motion planning and mobile manipulation in indoor settings. So David mentioned most of this stuff in his talk on URDF. There's a few simple shapes you can use, from cylinders to boxes to spheres, which are all built into Gazebo. And then you can incorporate 3D meshes from various sources. You can either make it yourself via SketchUp or Blender or SolidWorks or your favorite tool, or download it from the Google's 3D Warehouse, which has been a great resource. And if you want to create height maps, just load up your favorite image editor and create a grayscale image, and Gazebo does the rest to interpret white values as high and black values as low. So a word on meshes. These can be problematic for people to use, mostly because there's a lot of different parameters that you can mess with meshes that can have bad effects when you bring them into Gazebo. So the one thing to note is that Gazebo is not a 3D modeler. So you should use SketchUp or Blender to do all that kind of stuff. Gazebo will just take in your data and use what it gets. So along those lines, when you export meshes to be used in Gazebo, it's always a good idea to make sure that they're at coordinate 0, 0, 0. This will make it very easy for you to position it logically in a world, and it'll make your life a lot easier. Gazebo itself doesn't have a defined unit that it lives by. We try to promote the idea that you use metric. It makes it easy for you to share models and worlds amongst yourselves, but you could use English units if you want. So it was previously mentioned something about creating texture maps and applying them to meshes and problems associated with that. I recommend looking up tutorials online. Blender gives you the most power to control textures and meshes, but it's also the one to cause you the most headache, so you'll have to decide what's right for you. But you should pay attention to how you set up your meshes in terms of ambient light properties, diffuse properties, whether your normals are correct. All these have effects on whether your models show up at all, whether they look light or dark, things along those lines. And you can go online and look through some of our tutorials and our mailing list, and I can give you lots of tips and tricks, but I myself am not an expert. This is getting into the realm of artist, and I'm not an artist. So when you're doing this, you should also keep in mind that these meshes are going to be put into simulation. So you don't want to have overly complex meshes and models, which will unduly slow down and negatively impact your simulation. So keep an eye out for really high polygon counts, and you can play certain tricks, like using light maps to make low polygon count models look really good. And again, there's tutorials online that do this for you. We'll tell you how to do this. So you can organize your resources on a per project basis. All you need to do is create a directory structure with your models and your materials and textures, and tell Gazebo about this by either using an environment variable or using an API call. Both operate in the same way, and you can adjust this as you need for your various projects. So another note on efficiency. When you're creating your environments, anything that doesn't need to be simulated dynamically, as in it doesn't need to, let's say, roll when you push it or fall down, you should define this as being static. This bypasses the dynamic update step in the physics engine. It's a lot more efficient at the cost of it doesn't actually have mass or inertia and any of those properties. However, you can still collide with it. And recently in Gazebo 1.0, there's an animation engine which lets you animate these things. So you can still move them around through a programmatic way via a plugin or a topic. When you're constructing models, you can construct them in a variety of ways. So this is a very simple example of a table. If you want to attach the top of the table to a set of legs, you can use either joints, which add additional constraints to your system and therefore slows everything down. In this case, it's kind of silly to do that because the constraints are ideally 0 at all times, so it has to solve this very rigid, stiff constraint. So ideally, you would make this as a composite link that is composed of multiple collision objects, which improves efficiency and still maintains the same behavior. And of course, in the ideal world, Gazebo looks exactly like the real world. We're not quite there yet. So this slide is mostly a set of pointers to go by when you're sitting down and creating your own worlds and you don't bang your head against the wall. So start out simple. That's #1 rule of thumb. Slowly add things to your environment so you understand exactly what you're doing and how different parameters affect the way Gazebo looks and how it acts. So things like start with one light source. It's amazing how far you can get with one light source, and I see lots of worlds all the time with 20 different light sources, and they wonder why things look strange. So if you're familiar with vertex shaders and per pixel shaders, you can easily add these in, just put them in your resource path. Ogre and Gazebo handle these nicely. Just use them as you will. If you want to contribute back, please submit patches. I love new fancy visual effects. If you want to add some more interesting features like a dynamic sky, moving clouds, that's all taken care of for you in SDF. And you can add fog and various parameters of that nature to give a sense of distance and depth of field. So at this point, I'm going to hand it over to John to talk about robot modeling.
All right, thanks, Nate. That was a good introduction for Gazebo, I think. And I'm going to talk a little bit about robot modeling. Specifically, it's quite a bit of effort to build a good representation of a robot in simulation. But before we start, I think we should probably think about what is a model. And it's obvious it looks like that. This is kind of the representation for a robot model in simulation. So basically, it's a collection of links, joints, sensors, actuators, and plugins. And you need most of these components to have a functional robot that can perform useful tasks. So if you're a physics guy like me, I consider a few balls on a spring robot model, and you can do this quite easily in Gazebo. Here is just a few spheres that are on this prismatic joint, and they're attached via spring at different frequencies, different spring stiffness. And let's see, yeah. And the springs can be simulated via the physics engine, or it can be done by a plugin. Another example is a simple robot arm, something like a SCARA arm. And you can actually hand code this in URDF with a text editor in about 10 minutes. That's one thing I like about URDF. But normally, you build a simplified version of the model for debugging purposes with as much few joints as you can and less visual effects. But Then you can evolve the model, add better looking visualization meshes, and add better collision meshes. And they can look much better in the end. So here, I think these models comes, if you check out Gazebo as of now, you should get all 3 of these robot models in the source code. All right, so maybe this is preaching to the choir, but why do we need a 3D dynamics simulator? And there are many simulation fidelity. There's many simulators out there for different purposes, things like Stage for 2D simulation. From a 3D perspective, a couple things that Gazebo can do, I feel like I should highlight, are the basically dynamic simulation. This means constraint rigid body dynamics with contacts. And there's some caveat, though. Given that we're based off of the open source projects, OD and Bullet, they are essentially LCP type of solvers. So there's this trade-off game you have to play between having a very accurate, quote-unquote accurate dynamic simulation and an efficient real-time safe simulation. So you can have the looks right, what I call the low-frequency dynamics, but interactive. So it's good for debugging your code running real time. You can look at the screen, you can adjust the teleoperation bar and see how the robot moves, and make sure that everything else through the chain of software commands gets passed down correctly. Or there's the non-interactive version. If you're not patient, you can crank up the accuracy of the physics solver and let it run overnight for regression testings, for example, or things like Monte Carlo simulations and types of analysis that you wouldn't do looking at the GUI screen. So in addition to dynamics, there's visual simulation, as Nate mentioned. We use Ogre to produce 3D images, range, depth, sensor data. And lastly, to tie everything together, closing loop between visual and dynamic simulation, that's one of the benefits you get from a simulation engine like Gazebo. So I guess to avoid simulationism, where you debug your code, you build your model, you test everything out, then you pour everything to the robot and get some totally unexpected result. It's important to understand, I think, the underlying processes that's going on inside a simulation engine. I just want to highlight some of the main points I think that are important. So in Gazebo, the equations of motions are modeled by the Newton-Euler equations. And it's using a first-order time integration, which means your air bound goes down linearly with the time step size. The constraints currently are frictionless joints. They can be revolute or prismatic, as David mentioned earlier with the URDF intro. And collision in simulation, right now, the OD and Bullet can do inelastic collisions quite nicely, but elastic collisions are still something that we need to work on to make it better. And lastly, for contact dynamics, the friction is being simulated as a friction pyramid rather than a perfect friction cone, and that's for efficiency purposes. All right, so once you start modeling the robot, there's a couple, you might have seen words like URDF and SDF thrown around. I wanted to talk a little bit about URDF was developed as a efficient subset of information about robot model that's needed by various components in ROS, such as TF, such as the robot mechanism control or motion planning or simulation engine. And on the other hand, SDF is written for Gazebo specifically. It accounts for more things like lighting, sensors, physics, scene, OpenGL descriptions, shading, for example, are all encompassed in the SDF redundant, but SDF. The main differences between URDF and SDF, you have a tree structure requirement versus a graph. where in URDF, right now it requires that the kinematic chain is a tree, which means every link has only one parent. The transformations are defined in a way that the parent of the link is another parent. And I want to mention this because in SDF, all the links inside the model are parented from the model coordinate system. So in ROS, there's URDF to SDF converter in the ROS package, and all the details are on the wiki that you can look at. Currently, there's some of the models that I mentioned earlier and simple ones that are shipped with Gazebo. And of course, we encourage people to contribute by either email or patches. And hopefully soon we'll have an online model database that we can use for people to submit models more easily. Okay, this might be very basic, but I thought I should mention it briefly. So what's inside of a link? A link is defined by inertia, collision, and visual. And the inertia term is essentially just the M in F equal to MA. The collision geometry is used by the collision detection algorithm to generate contact joints, which are fed to the physics engine for updating dynamics. And, and lastly, the visual geometry, which can be specified separately, is used by the rendering engine to generate images for either GUI or for the camera sensors in your model. So a little bit about joints. Again, this is rudimentary. And there are user-defined joints, which are usually constraints on degrees of freedom between links. They can be prismatic, revolute. There's a revolute 2 joints, which were designed for car-like suspension constraints, and other ones, such as universal ball screw joints, which can be defined in your SDF or UIDF. I believe, yeah, that's true. And also, there's dynamically created contact joints. So these are, again, created by the collision detection engine and generated and removed dynamically at every update cycle. So sensors, Gazebo supports a few sensors right now. There's the camera or Connect sensor, which generate images in point clouds based on the GPU. There is a laser range sensor, which gives you the distance to an object, simulating a laser ray trace. That can be done in both CPU and lately there's a GPU implementation for it. Depending on your resource allocation needs, you can shift it around. Also, there's contact sensors, which gives you back the collision information, such as the forces at the contact, the normal, the contact position, and such. And the last two, the RFID sensor, which gives you back kind of the relative model position information. And the force torque sensor, which gives the force approximation at the joints right now. We're looking to extend that to a more general force torque sensor in the future. So another thing to keep in mind when building robot models, how to keep it efficient, especially a lot of the application requires real-time or near real-time performance. There's a couple of main bottlenecks that I listed here. They are physics, collision, and rendering. So the physics, which is CPU-based, basically it's driven by the number of joints in the model, which could come from either contact joints or user-defined joints. In general, it's a good idea to keep the number of joints to a minimal, if you can. Also, if you model a closed-loop kinematic, obviously it's going to take longer to solve than a tree-like structure. And for collision detection, the one thing to keep in mind is that geometric primitives are much more efficient for the engines than a tri-mesh. And this is obvious because you have to compare you have to go through the list of triangles of a tri-mesh when you're doing the collision detection. So either you try to use primitive collision geometries or keep the number of tri-mesh as slow as possible. And this, as a rule of thumb, I put this number 5K. That's based on my desktop for the PR2 running in real time per link. So that number may vary, depends on your computational resource. Similarly, for the GPU, if you have a tri-mesh a rendering visual, you want to keep the number of triangles low. So since that the image sensor generation is done by the GPU, that is also potentially could be a resource-intensive process. So if you're trying to simulate a 5-megapixel camera in simulation, you can't expect a 20 hertz update rate, for example, on a desktop. So in case that the accuracy of dynamics is important to you, there's a couple things I want to mention of how to make the simulation more accurate. And since we're currently stuck with the maximal coordinate formulation for dynamics, there's the few things we can do are controlling this time step size. And how to pick a time step size for a dynamic model. Typically, this is driven by something like a dynamic controller on your robot. So if your MCB is running at kilohertz, you probably don't want to go pick a lower frequency than that. So for example, the PR2 is 1 kilohertz. The PR2 simulator is currently set at 1 kilohertz for efficiency purposes. And it turns out that we didn't have to change the PID gains for most of the joints, probably by luck, and that PR2 is a pretty dynamically benign model. But if you decrease the time step size, as I said, the error decreases linear with DT, and you can get a better model, but with the cost of performance. So on the other side, there's many parameters in the solver that you can tweak to make things perform better. One of the obvious ones I want to point out is this iters parameter, which is essentially the number of iterations for the constraint force satisfaction algorithm. And you can look it up if you're curious. I think there is some documentation on the wiki on how the inner workings of these LCP type solvers. There's probably a lot of documentation. And the last point is that if you're modeling the physics, there's a certain amount of omission that is done when you model a robot. So for example, most of the joints the transmissions are not modeled on the PR2. They're simply a revolute joint, for example. And so with that, if you want better simulation, you actually have to go into the details of a joint and model the components. And again, that's going to be computationally heavy, but you can get better results that way. One thing I want to mention is for example, the PR2 gripper, which has a very low efficiency but high mechanical reduction joint. And to simulate that as a simple prismatic joint, actually it turns out to be less efficient than simulating as a screw joint, which has two components, a rotational and a prismatic portion. So those are the things that kind of makes a lot of difference when you model robots. So now that, suppose you have a robot modeled in simulation and it's up and running, you hit the start button, the robot sits there, maybe the arms fall down, that's pretty much it. Inside of Gazebo, we have a convenient tool for you to interact with the joints. You can specify joint torques and you can specify PID terms on velocity and position for each of the joints into the model. So it's a nice quick test to make sure that things are moving correctly, the joints are in the right locations. And to move forward with simulation, normally the next step is to come up with a programmatic control. So you have to decide what level of abstraction is needed to model the robot's software input I/O. Again, take PR2 for example. Things are broken down at the ROS level. So the plugins in the simulation essentially broadcast the same interface in terms of ROS topics and services, which means all the higher level components can be reused with minimal adjustment. And the way to program the interface, the best approach is probably to use plugins. As mentioned, or we'll cover this later on, but there are different levels of plugins. World plugins, which give you access to all the models inside of World, or model plugins, which has a narrow scope, essentially just the model that you attach it to, and you have access to the links and the joints. All right, so last few slides on robot modeling, I want to mention some of the common pitfalls that people see in simulation. And there's a video there. Before I play that, yeah, I can go on this. There's, because the visual and the collision meshes are decoupled, so a lot of times things come up mismatched with wrong scale, or the joints are located incorrectly. So there are nice visualization tools inside of Gazebo GUI that let you view things and make sure things are right. This is an example of what I call self-uprighting cup. And what happens is you model cups or plates and you try to tip them over, they come back on themselves. So that's, usually this is caused by things like CG being outside of the body of the model. And again, you can visualize CG location. So the GUI is a pretty handy tool for first order debugging. So from answering a lot of the answers.ros.org questions, or this is kind of what you see typically. You start simulation and your model disappears. And then you look around and later on it falls down somewhere else far away. So I blame this on the interpenetration correction of the physics engine, and there's been some work done to try to make that better in the future, in the near future. And these videos are unrelated, I know. But so that's what the, so when you bring up the GUI, so the way to fix this is either you start up the GUI and you step through the simulation one step at a time to see where the penetration occurs, or basically spawn your object away from all the other objects. So this example, I don't have a nice video of. Didn't bother reproducing. But in the beginning when we started the PR2 simulation, or I'm sure a lot of you have seen this, where you model your robot, you start simulation and the arms kind of twirl around in a crazy way and the robot dances around. There's a few bugs that were fixed along the way to make that behavior go away, but you can still do it if you use improper values of inertia, so you have a plugin that applies too large a force to the body parts. And most of the time you can isolate the problem by disabling the plugins, or you can do it by decreasing the number of time steps and stepping through the physics slowly to see where the instability originates from. Some of the harder to fix problems with the physics engine, and that's kind of the quirk of this LCP style solver, is that, as I mentioned earlier, for numerically stiff systems, or if you have connected body with large mass ratios, so you start simulation and the things are just jittering around non-stop. So if you look at that pendulum in the car. So you can fix this one of several ways. One is by reducing the stiffness in your system by, so ODE has this blurb that recommends all the mass be unit masses, but you don't have to go to that extreme. But you can help by just knowing if you're connecting a 1,000 kilogram body to something that's 1 gram, and then you kind of expect the system to be much stiffer. You can correct it by increasing the number of inner iterations for the solution. So that's where that ITER parameter comes in handy. Or you could do it by decreasing the time step size. And that's kind of the two main things that I would recommend tweaking with if you're having trouble with the getting correct dynamic behavior of your simulation. Okay, so I'm gonna hand back to my colleague Nate to finish up with some of the Gazebo interfaces.
Okay, thanks, John. So the last bit that we're going to talk about, is how to interface your code to Gazebo. So ideally, you have all these environments and models, and you want to do something interesting, fun, and cool with it. So how do you go about doing that? We've mentioned plugins, which gives you a lot of control over Gazebo, and it can also come at a certain expense, so you can do lots of bad things, but we figure it's better to let you have complete control than too little control. So there's 4 different types of plugins that you can use, one being system-level plugins, which are loaded directly from the command line. So these are actually loaded before Gazebo begins its initialization process, so you can control exactly how Gazebo is brought up, let's say. World level plugins are a little bit more low level, so a world that is spawned and has stuff in it, you can create a plugin for that and control all the models in the entire world. A little bit lower is a model level plugin, which is probably the most common plugin that you'll deal with, and this is a plugin that's directly connected to a specific model within the world. And you can do things like control the position of a model, set its velocity, control the links to do things like have a differential drive or inverse kinematic controller, let's say. And slightly analogous to that is having a controller for sensors, so you can do things like pass data around, apply noise models, or any kind of filtering that you want. So there's lots of documentation on how to create plugins. I'm not going to go into the C-level abstraction of how to go about doing it, but it's a very thin wrapper that requires just a few very specific lines of code, and then you can do pretty much anything you want. So there's 2 sets of plugins. There's Gazebo-specific plugins that exist in the Gazebo sources, and there's ROS plugins that act as a bridge between Gazebo and ROS. So that interface is pretty minimal. It's essentially taking data from topics and services and translating them into a format that Gazebo can understand and use. So if you happen to have or develop plugins along the way, please contribute them back either in ROS packages or to the Gazebo website and through track on there. Oh, and in the future, along with the model database, we're going to have the option to upload and browse people's plugins so that you can see what people have done in the past and contribute plugins for specific models or worlds. So we're going to group source this thing. So the other way you can talk with Gazebo is through inter-process communication via sockets. So this is extremely similar to ROS. In fact, when we rewrote this, we pretty much had ROS and then Gazebo and did a lot of copying. So it looks very similar. So if you're happy and familiar with the way ROS works, you can get up to speed pretty quickly with the way Gazebo works. The main difference is that we use Google protobufs to do our message passing and serialization and all that stuff. So when to use topics and when to use plugins. So topics are great if you want to run the server remotely and you want to run your code on some other location. If you want to start and stop your client code many times and let the server keep running, then you probably should use topics. If you want direct low-level control to the way Gazebo operates, you should probably use plugins then. And typically what people use is a combination of these 2. So you write a plugin that does something specific within Gazebo, expose that through a topic, and then have some code talk to that plugin via topic. So unrelated to topics and plugins, we had to throw in a slide about the various command line tools that we have available. So similar to ROS topic, there's a GZ topic to see exactly what topics are being published, the information about them. If you want to see the current status of simulator without bringing up the GUI, you can run GZ stats, and that gives you all the information about performance, whether it's pause, running, that type of thing. GZ Factory allows you to spawn and remove models from a running simulation. And this is very similar to the Gazebo Gazebo version in ROS of spawn model, but this takes URDF specific code and spawns it into Gazebo. And if you want to generate, take URDF, convert it into a Gazebo format, you can use the URDF to model. So there's lots of places to get help, from answers.ros.org to our mailing list, to the wiki and the tutorials online. You can ask me today and tomorrow. Anything that you want to contribute or work on, let us know. We're happy to help in any way, shape that we can. So with that, are there any questions? The question was, can you parameterize plugins? Yeah, so the way plugins are defined is it's a single line of XML, and you can put in any amount of XML tags within that element that you want and read it in your plugin. So you can reference other links within a model, you can reference other models within a world, you can put in your own custom parameters. So for example, there's a diff drive plugin, and you can specify parameters that are along the lines of which links are the wheels and the wheel radius size, and go from there. This question is, can I talk a little bit more about the human character model in Gazebo? So that video was ongoing work of an intern at Willow Garage called, his name is Mihai Dola from University of TUM Munich, and he's integrating the ability to take motion capture data and apply it to human skeleton mesh and animate that. So we're currently at the point where we're at the level of working out why a model jitters a little. So it's like 95% done. Within the next release, you'll have complete access. So if you take, say, the CMU motion cap data set or create your own data set, you can apply it to a model within Gazebo and have characters walking around. So any support for distributed simulation? That's a great question. So distributing the physics engine is somewhat complicated, and you could think of it in terms of breaking it apart in a few different ways. You can either distribute, say, the models at different machines, or you can segment the world into different locations. We've talked about this off and on. However, the most bang for our buck is currently optimizing our current physics simulations, and once we enter the realm of, well, we have no more room to go in terms of computational power to simulate the environments that we need, then we'll have to start looking at how to distribute it, but it's a hard problem. So sometime in the future maybe, but not right now. So the question is, in the old Gazebo, we could specify a mean and Gaussian to add noise to a model. Right now, it does not exist. However, creating Gaussian noise is fairly easy. So the tools to do it are there. If you send an email to the mailing list, that means I'll work on it faster. And you can contribute patches, yes.
I think in the ROS plugin, there is a parameter for Gaussian noise for some of the, I believe, the position data that's being generated. So you can certainly write a plugin that takes in those parameters and have your own simple model that adds noise to the data coming from Gazebo.
Okay, we have two questions, so I'll take one from this side and one from this side. Go ahead. So the question was, have people done more sophisticated work in terms of adding noise that's not Gaussian to mimic real-life sensor data? So the most that we've done internally is being able to produce bare images of that nature. That's not necessarily a noise model per se, but we haven't received any word of people doing anything more complex. That's not to say people haven't. It just hasn't come across my radar yet. Yes? So the question is, can I happily run Gazebo on my laptop? It's unfortunate you said happily. So it depends on what you want to get out of the simulation. So I have a laptop that's 2 years old, and I can run Gazebo on it. You have to set your expectations appropriately. So if you want to generate the full PR2 sensor suite of data, you're not going to be happy. If you want to simulate some basic things, maybe use the animation engine or a single camera or things along that nature, then you might be happy. Okay, I think that's it. So, thanks.
Thank you, everyone. We now have a break for a half hour, so we'll be resuming at 4. Just a reminder, if you'd like to do a lightning talk, please catch up with Ken Conley by the end of the break. And also, we know that the day's getting late. The talks are going to be going faster and faster until we get the 3-minute per talk at the end of the day.